Super great to be here. Thank you for organizing this very first hardware day as well. So I'm Michiel, co-founder of Belfort, and I'll start the talk with actually a very short introduction to Belfort. Belfort is a spin-out out of COSIC Leuven. At COSIC, we have a very long history of working on FHE and hardware for FHE. This actually started back in 2015 when we did the first implementation of a Yashi. I think that's a scheme probably a lot of the people on this talk won't be familiar with. This was also before my time at COSIC actually. But since then, we've also worked on almost all of the different schemes. It includes BFE, BGV, CTTS, TFHE. So a long history and tradition of working on hardware acceleration for FHE. We actually came out of stealth, semi-stealth as a company yesterday, coincidentally, where we announced our fundraise and really announced that we spun out of the university. We've raised some money, $6 million to bring our hardware to the market now. Our team is currently 7 experts in cryptography, hardware, and software, and we're looking to extend that soon. So I thought I'd use this talk as well to put that out there. If you're interested to join our team, definitely make sure to scan this QR code here and have a look. Okay, so with that short introduction to Belfort, here's the agenda for today. I did decide to keep 2 generic slides at the start, talking a bit about encrypted computing and fully homomorphic encryption. I'm sure many of you on this call are very familiar with all of this, but in case there's some that might have less background in FHE, I thought to start with 2 generic slides on homomorphic encryption and why we're really all here, of course, today. So at Belfort, yeah, we fundamentally really believe that we need secure computing technologies to handle these new applications on very sensitive data. We believe that the trust guarantees provided by things such as public clouds, public APIs are not sufficient for the high sensitivity data that we have in healthcare, finance, legal, all those sectors that process high sensitive data, of course. Different ways to do computing on encrypted data, different ways to do confidential computing. We, of course, and I think everybody here on this call and on this day are strong believers in the cryptography, in fully homomorphic encryption, which is the only technology that makes this entirely trustless. If we look at some other technologies, let's take the example of trusted execution environments, where there is the need to trust the hardware, where there is the risk of side channel attacks. We feel those are things where FHE definitely has a step ahead. But of course, one of the main drawbacks of FHE, and that's why we're all here today and why we're talking about hardware, is that it is so slow and costly. That's why typically indeed generic software is not sufficient, why we need dedicated hardware accelerators. And that's of course exactly part also of what we are doing at Belfort. So onto Belfort's hardware roadmap, a very generic overview of what type of compute platforms you might be using to accelerate FHE. And I think, yeah, we at Belfort, and I think most people on this call are mostly interested on the ones on the right here, the ones that are really considered hardware architectures, the ones that give you the most efficiency, the most energy efficiency, but at the same time, you're giving up some flexibility, you're giving up some design time. Photonics is missing from the slide. Maybe I should have also added that. Might put that on the right-hand side of ASIC. That's where you get the energy efficiency all the way, of course. So at Belfort, we are first focusing on FPGA. Our first approach is FPGA first, and the reason for that is mostly due to flexibility. On FPGAs, we can reprogram the design. We can adapt it to changing FHE schemes. We can adapt it to changing parameters. And that's why we've always been big proponents of starting with FPGAs first before moving too quickly into ASICs. At the same time, of course, ASICs is where the largest efficiency gains on both energy and performance are. And ASICs are definitely part of the roadmap of Belfort as well. We aim to have an ASIC out in 2028, basically the continuation of our FPGA architecture and achieving even further greater acceleration than we already do on FPGA. So today, what we can achieve on FPGA is we're typically a factor of about 5 times faster compared to a 64-core multi-threaded CPU. These numbers here are from a transciphering benchmark. We have other benchmarks available. More on that later in the talk as well. What's important here is we always compare to multi-threaded CPU implementations. That's sometimes not the case if you look at academic work. Sometimes they might compare against single core. We believe multi-core CPU is often the best benchmark, the best comparison. So today on FPGAs, we're about a factor 5 times faster, 12 times cheaper, and about 30 times more energy efficient than on multi-threaded CPUs. We have a roadmap at Belfort to first improve our FPGA architecture. We're already on that roadmap as well. In early 2026, we expect another significant performance improvement on the FPGA architecture. But then finally, as I mentioned, we are on a roadmap towards ASICs as well, and that is where you get even larger efficiency gains, even larger cost advantage as well. Very shortly on the Belfort FPGA architecture, and I'm not going to go into too much detail here because I've presented this already a few times. The first time we presented our architecture was actually at an FHE.org event. That was the one in Tokyo, I believe, in 2023, where we also showed a live demo. But so what we really do, what the fundamental technological breakthroughs are in the Belfort architecture, is that we work with a specialized streaming architecture. We combine that with a batching approach where we process multiple ciphertexts in parallel, and those two together really make sure that we achieve 100% utilization of all the units that are on the hardware. This is really, I would say, the sort of core design philosophy we have. We try to maximally make use of the hardware that we instantiate. And 100%, yeah, is really the goal we're striving for there, making sure that all of the hardware is doing useful work at all times. At the same time, these techniques that we introduced, they allow us to work with modest memory storage and modest memory bandwidth, which is a very significant advantage we have as well. The fact that we don't need massive off-chip memory to be able to supply data to the chip. As I mentioned, our technical roadmap, we have further speedups first planned on FPGA, and we're also working on extending the architecture towards multiple schemes and multiple parameters. Historically, we've always focused the architecture on TFHE first, but we're now adding support for the other schemes into the architecture as well. As I mentioned, we have a lot of experience at COSIC, spinning out of the research group and working on all different FHE schemes. So that expertise we're now integrating into the Belfort architecture as well. So one thing I also want to stress in today's talk is the fact that our hardware is available and that we're looking for users. We're looking to make this as simple as possible to use, and we're looking for the early testers that are helping to refine the roadmap together with us. So one of the advantages as well of going for FPGAs first is that we can take this architecture that we have and compile it into an FPGA bitstream and FPGA executable. This executable is today already live on Amazon Cloud. So if you go to Amazon Cloud, you search for the Belfort FHE accelerator, you can find it there, you can program it onto the Amazon FPGAs, and this is all ready to go out of the box. We've always focused on making this as simple to deploy as possible, as simple to use as possible. Hope to show that on the next few slides as well. But so this is really something to stress. This is available live out there. A funny side note there as well, you see view purchase option here on this slide, but for now, this is still entirely free. We're looking for the first test users. If you want to deploy this, you can go to Amazon Cloud and have this live and ready there. To make that even more clear, if you're a user that's already running on Amazon, for example, on the left here, you're typically using an FHE software library. You're running this on a CPU machine. What we really simply do is we provide the executable, the software drivers as part of this Amazon machine image. You can enable all of this and you're running immediately with the Belfort FPGAs. It's a three-step process. You start up the instance. You can choose for 1 FPGA, 2 FPGAs, 8 FPGAs. We support all of that. And we have some code examples later. It's also really easy and straightforward to switch between one or multiple FPGAs. Then you connect to this instance, and then you will finally clone the Belfort repository and run some applications that I have some slides on later as well. So about applications, about like how might you now test this, how might you now use this. In terms of software stack, we support 2 software frontends. The first one is the Google Hair compiler and the Google FHE on Cloud framework. Not going to go too much into detail here because there's a whole talk from Google. I believe it's the final talk of today, where Shruti and Wouter are going to give you many, many more details. But that is something where the Belfort FPGA is already natively integrated. There is both the Google FHE Cloud framework, where you can find some instructions to launch cloud instances, also including the Belfort FPGAs. And then there is ongoing work to have the Belfort FPGA really integrated as backend into Hair. We have the first examples there as well, and there's ongoing support to further improve this. Again, not too much details now. Shruti and Wouter are going to tell you much more about this later on as well. The second frontend we support is the TFHE Rust environment from Zama, and that is one that we've always supported and tried to make as simple to use as possible. And I hope this very small code example on the slides here prove that. We've enabled FPGA acceleration through just 2 lines of code changes. On the left is a default execution where you're generating keys, sending those keys to the server, and then you might run your favorite application, which in this case is just a multiplication between 2 ciphertexts. On the right-hand side, the only thing you need to change if you want to run with Belfort FPGAs available is to use this FPGA key that we defined and send that FPGA key to the server. All of the rest is just staying identically the same. You're still just writing your application in the way you want, and everything gets offloaded to the FPGAs and is automatically taken care of. There's a link here to our repository as well. What this includes is first the patch so that the Belfort APIs are added to the library, and then second, all the instructions to run this on the Amazon Cloud FPGAs and using some applications as well. We've already onboarded 2 first test users to this. They warmly recommend going through the flow. They helped us catch the first few bugs in the architecture as well. They helped us catch some bugs that prevented them from using the FPGAs efficiently. But all of that has been ironed out, and that's why we're now very excited to onboard more users onto the Belfort FPGAs and very excited to work with you. Right now, you really still have the advantage as well. Like the team is very available to help you with the first early bugs. Is very excited to help you onboard your applications. So definitely, if you have some of them, feel free to go to the repository, launch an instance, and ping us if you need any help with something. Final part of the talk, focusing a little bit more on those applications. So in the first, the last slide I just covered, that was really for the power users that might have their own applications available. But if you don't fall into that category, we also already have 4 accelerated demos available. These include edit distance calculations, AES transciphering, trivium transciphering, and confidential payments. On this slide here, I compared the execution again to a 64-core CPU. We're about 4 to 5 times faster on the FPGAs versus using the CPU with all their cores. And an added benefit you really get here is the price reduction. Shown at the top of this slide here, on the FPGA, you might only be needing, you only need 400 per month because this is 400 euros per month because this is much more energy efficient. The CPU in this comparison is also much more costly. So you're not only getting a performance advantage with FPGAs, you're also getting a price advantage for your application. A little bit more in detail about each of the applications. So starting from the right, confidential payments. This is an application you might be using in a blockchain situation, for example, where you have one user sending a transaction to another user, and there is some checks on the balances. Trivium transciphering. This is the Trivium implementation that was originally developed by the Zama team, where we integrated FPGA support as well. AES transciphering is a new one we recently implemented. This is also implemented because it's a very relevant benchmark, we feel, to compare different implementations. AES is, of course, a cipher that many people are familiar with, and we integrated FPGA support, tried some new algorithmic improvements on FPGA as well, and so those are live as we speak as well. This was implemented by our summer intern, Beren. Big shout out to her as well for implementing this as part of a summer internship at Belfort and at COSIC. And then edit distance, a very exciting, very interesting application. Not going to go into too much detail because we have the main author of that work, Wouter, also presenting in the last session. He's even going to give you a live demo, I believe. So I'll give Wouter the honor of telling more there. There is one thing I do want to mention about the edit distance calculation. And I think that also continues a bit the discussion of the last presentation, is the advantages of hardware-software co-design. So this edit distance calculation is an application that we developed in collaboration with Swift. And as I mentioned, Wouter is going to show this live later. But Swift had this issue of trying to do certain analysis on encrypted bank transactions flowing through their network. What we did for them is first run their application that they were interested in through a compiler. And we saw that, the run times we achieved there were really still completely prohibitive to consider deploying this. That's where the team first started with software improvements. Wouter and Peter and Ingrid managed to greatly improve this there together with the Swift team. First in software, and then finally integration with the hardware is where you get the further massive speedups. It's these type of applications that we're very interested in at Belfort as well, ones where there is really the opportunity to co-design the hardware and the software, and where each can benefit from both approaches, where the hardware can be tweaked to the software application, and where in the software side, there is a lot of choice, a lot of possibility for algorithmic improvements that can then make it so that it maps better to the hardware. That actually brings me to my last slide, a bit of a call to action. If you're a developer, if you have FHE applications, definitely make sure to test them on the Belfort FPGAs. Try out our hardware accelerators. They're live on Amazon Cloud. You can go through this flow that I showed earlier. All of this is live to be prototyped. Secondly, if you have an exciting application and you're very interested in hardware-software co-design, where this application might be optimized for hardware execution, and at the same time, you want to get the latest performance improvements, you want to already get a feel for how this runs on hardware, contact us, because this is exactly the type of project that we are looking for, that we hope to execute. And then finally, if all of this in this talk is making you excited to potentially join our team, we are actively hiring around multiple roles that include software, hardware, and also on the operations side. So definitely make sure to have a look and make sure to apply. Okay, that concludes my talk. I'm happy to take any questions.
Okay, great. Thank you very much, Michiel. We have a few in the chat. So let me have a look. We might be able to get through all of them. So the first one is, can you share what's the latency to compute an AES encryption homomorphically?
The latency, out of the top of my head, on one FPGA, it is about 2 milliseconds currently. Wait, is that right? Or is it 2? I don't know the numbers out of the top of my head. I'm sorry.
No worries. Okay, so the next one from Sanu is, you mentioned a 10x speed up going from current FPGA implementation to an ASIC. Can you comment on what may be limiting ASIC performance? Is it inherent parallelism or memory bandwidth or something else?
So this is an estimate we have based on also a big parameter there, of course, is the ASIC technology node, where Later, more new technology nodes might result in faster speedups, whereas more conservative nodes, which are cheaper but might result in less speedups there. One significant advantage that we feel we have in our architecture is that it's fully compute bound. And that's typically a nice situation to be in when you do hardware design, because compute scales much better than memory. If you're memory bandwidth bound, there's only so much you can do after you plug HBM onto the chip. That is typically where you run into the memory bandwidth bottleneck. So for us, I think the 10x on ASIC, I would say, is a conservative estimate still. We keep this estimate because we're also still evaluating which technology node is most interesting for us. But we're definitely hopeful and optimistic that we'll achieve even further speedups there.
Okay, great.
By the way, for the AES implementation, the results are fully in the repository as well. So have a look, benchmark it yourself, run it yourself. I believe the results were 2 seconds per AES transciphering.
Cool, thanks for that. Okay, so the next one, there's quite a few more. So the next one, have you thought about embedded FPGAs as a potential middle ground between the commercial FPGAs and hardened accelerator ASICs you are designing? So he says they can have a good balance of flexibility and efficiency.
Definitely part of the things we are looking at. I think one of the things, and I believe this is maybe a topic that might be discussed on the panel as well, is flexibility is, of course, an important parameter. FHE standardization is still something that's going on. I think all of us here know that there's also a lot of advancement still on the cryptographic side, on the parameter side. There's still new schemes coming out even at the same time. So that is definitely something we're actively looking into at Belfort. This is also, I would say, one of the core strengths of the team. We really have a lot of expertise operating at the intersection between the cryptography and the hardware. And that is why flexibility is definitely high on our roadmap and on our priority list. And as part of that, embedded FPGAs that still have flexible units that can be reprogrammed, definitely interesting. Haven't made the decision yet if that is something we'll work with.
Nice. Okay, so there's 2 more for now at least. So the first one, which techniques have you used to achieve / show 100% utilization?
So that's really these 2 techniques that I highlighted on the slide. The first is this streaming architecture. And what makes a streaming architecture really different from a classical CPU architecture is that we are not constantly shipping data between memory units and compute units. We don't really have like a central register file where we're constantly sending data back and forth to the arithmetic units, but really everything is processed as a sort of pipeline that's continuously in use. The analogy is with a pipeline in a car factory, right? Where you have workers sitting at a belt, and because everything is going on this belt, everybody is doing useful work at all times. The second thing we couple with that is this batching technique that we introduced. And that is really one that is crucial to achieving this compute-bound nature of the design, because without that, we would very easily run into memory bandwidth issues. And because we are compute bound, we can achieve 100% utilization. If we were memory bound, we would have to be waiting for the memory to fill up the internal storage elements.
Nice. And the last one, I think, has already been answered by Furkan in the chat, but I will ask it anyway. What is the FPGA key and how is it generated?
So the FPGA key is really just a convenient wrapper, I would say, so that the operations are actually done on the FPGA. The FPGA key is not a different key from the key that you're already using, which is the bootstrapping key that you generate to do your operations. It's just a convenient handle so that when you set that one, all the operations are executed on the FPGA. So if I bring this code example up again, setting this FPGA key as the server key really makes it so that when you do this operation below, this gets offloaded to the FPGA automatically. but it's not a fundamentally different key than the one that you're already using on CPU. It's just a convenient way of making it so that this is easy to use for developers.
Okay, great. Well, I see no more questions in the chat. So Michiel, thank you very much again for the talk. It's very interesting. Maybe just one short one from me. So Belfort itself, where is the office going to be based? Is it in Leuven, or do you plan to base somewhere else?
Yeah, the technical team is mostly based out of Leuven. We actually have one team member in the US as well. But the technical team is in Leuven. We feel Leuven is an excellent team for cryptography. Leuven is an excellent place for cryptography research, which I'm sure many on the call here will agree with. But at the same time, Leuven is also a very good place for semiconductor design. We have IMEC right around the corner. We have several semiconductor companies in Leuven as well. So we're very optimistic. It's a very good place to be with the company, and we're definitely looking forward to further building the team there.